So today's lab is lab number 5. It's called Hooke's Law and Simple Harmonic Motion. Pretty easy lab, kind of fun. So I have to talk about springs. So here I have a spring hooked up to something like a wall, and it's attached to a mass, and you might want to pull that mass and stretch the spring. And so we call the initial position x naught, the final position x sub f, and then the change in position, delta x, would be final minus initial. And so Hooke's law says that the force that's going to pull back on this guy, the spring force, is equal to, well, it's proportional to k times the distance we stretch it. So the more you stretch it, the bigger the force. Where k is a constant, it's called the spring constant. So where k is called spring constant. All right, and this minus sign is just a reminder that it always pulls opposite of the displacement. So if you pull it to the right, the force is going to be to the left. So this sort of minus x hat is the opposite of the x direction. So this would be the x direction. It's pulling in the opposite direction. So you can either memorize that or you can do it with vector notation like this. So basically the magnitude of this guy, this vector, is just k times the displacement, where it's always opposite of the displacement. It's the force. Any questions so far? All right, so a high K or a big K, large K, what do you guys think that means? So if I have a larger K, that's going to give me a larger force, right? So another way of saying that is it's a stiff spring. And a small k, what kind of spring would that be? What's the opposite of stiff? Oh, soft. It's a soft spring. So one thing I want to emphasize is that k is a characteristic of the spring. So if you have a spring, it has a certain k associated with it. All right, so let's do a little plot here. And I want to plot force versus displacement. What would that plot look like? Yeah, so let's just do the magnitude. So in this case, it would be the bigger the displacement, the bigger the force. And obviously, the force is opposite of the displacement, but the magnitude gets bigger.
Is it curved at the bottom? Or is that just
No, that's just me not drawing a straight line. It's supposed to be as straight as possible. What would the slope of that curve be, by the way? Or that line? Rise over run. K, good. So the slope will be K. Very good. All right, so if we hang it from the ceiling instead of this horizontal, we'll have the initial situation where the spring is all coiled up, kind of sitting there, and we call that y naught, because it's unstretched. It's the unstretched position. And then the final position is after it's been stretched. Wherever you measured it on there, you measured it on here. And then the displacement would be final minus initial. All right. But I want to draw the forces on this object here. What are the forces that are acting on this guy? Good. Force of gravity is pulling it down, which happens to be equal to mg. Is there any other forces? Yeah, the spring force pulling it back up, which we happen to know is magnitude is k times delta x, but in this case we relabeled it y because we're doing the vertical direction. So So the magnitude is this big, but the arrow indicates that it's in the opposite direction. So let's apply Newton's second law. What's Newton's second law? F equals ma. What if there's more than one force? Sum of the forces. So don't forget the sum. Is F a scalar or a vector? So this would be a vector. So I'm trying to train you guys into thinking of the full version of Newton's second law and not just the F equals ma part. Because this has two forces on it, right? And so if you ignore one of them, you're going to have a hard time figuring out what's going on. All right, so what are the sum of the forces here? Spring force minus the gravitational force, and that equals to ma, right? But in this case, I'm going to assume that it's just sitting there at rest. So is it accelerating? No. So this implies that the spring force is equal to the force of gravity, which you probably could have just guessed, right, by looking at the picture. So K delta Y is equal to mg. What happens if I double the mass of the system? What's going to physically happen to that spring? It's going to stretch more. All right, so let's plot that. Delta Y versus mass. So if I double the mass, I double the stretch. So linear. Any questions? All right, let's talk about simple harmonic motion. Does anybody know what simple harmonic motion is? Any guesses? No, guys haven't heard of this? Oh, it has something to do with motion, right? And it's also simple, so that's good. It's not complicated. What was harmonic? Anyone? Yeah, oscillating or repeating behavior. So it oscillates. So if I was going to plot something that oscillates, I might draw it like this. Specifically, I want it to oscillate in time. And call that the x position. The amplitude's a and minus a over here. Does anybody know what type of function that is describing this behavior? A sine or a cosine. The way I drew it, it starts up high, so let's do cosine. So x as a function of t is equal to a, the amplitude, cosine omega t, as this guy's oscillating with time. All right, what's omega? No, not quite, but you're thinking on the right track. This has to do with time, so time is more like frequency, right? So if there was x here, it would have been associated with wavelength. But this is a frequency. This is 2 pi times the hertz. So this is called omega. It's a Greek letter. It's not a W. Physicists get tired of writing 2 pi over and over again, so sometimes we use this omega. We could have put 2 pi f in here, but we're lazy. And f is related to the period by, does anybody remember? 1 over. So it's 2 pi over the period. What's the period on this picture here? How long would it be? top to top or from bottom to bottom. So this would be a T, or this guy would be a period. Any questions? All right, omega also happens to be equal to the square root of k over m, where k is the spring constant and m is the mass. And so if we look at this picture here, instead of assuming that it's at rest, we let it oscillate. So we pull it a little bit too far and then we let go. It's going to start to move up and down. And so you could time its frequency. And since this guy is related by this guy here, we can get that the period is equal to, let's see, omega over 2 pi, which is equal to, is that right? Omega over 2 pi? 2 pi over omega. You guys see what I'm doing there? So I multiplied by t and divided by omega. But we know what omega is. It's square root of k over m. So you get square root of m over k. Right. So if you time the period of oscillation, you can figure out what the k constant is. This is one way to measure the k of a spring, is to let it oscillate, see what its period is. Questions? All right, so let's talk about series and parallel. So here are two springs in series. Give them a K1 and a K2. You guys see that? And the question is what is the effective K of this system? So K effective. Any guesses? So if I have a spring and it's holding up this mass and I add another spring and it's holding up this mass, what's going to happen to the forces on this mass? Is it going to increase or decrease? Increase, because you have twice as many forces. You have a force from this guy called F1. You have another force from this guy called F2. So if these guys were the same spring constant and displaced the same amount, the force would double. So the effective constant is the sum of the two constants. Oh, sorry, this was parallel, right? Yeah, so when they're parallel to each other, it's called parallel. All right, then in series, K1, K2. Any guesses for this one? This one's a little more difficult. It's twice the distance, right? So the force should be less. So they have an inverse relationship. K effective is equal to 1 over K1 plus 1 over K2. All right, so just to show you a little demonstration of a setup here. So what's this displacement here called? Y initial or X initial. And then this much, that's Y final. And so initial, final minus initial is the displacement. Okay, so this whole thing isn't the displacement. It's, yeah. I have to always say that because people get confused. I know it seems obvious. All right, and so you can tell by how far it's stretched and how much weight you put on it what the spring constant is, right? The other thing you can do is you can put it into oscillation, time it, find its period. You know its mass, you know its period, so you can use this equation to solve for K and find its spring constant. And then you're going to compare the two spring constants from both methods, from stretching it and oscillation. Any questions? All right, you guys can get started.